Morning. Long time since we've talked. I'm going to do a short video regarding calculating emission and from and absorption for surfaces. You have a good general background on it, but the most general type of calculation we'd like to be able to do is if we have a diffuse surface. So I'm going to take you through those calculations. Just a couple quick notes. First of all, be really good before you do this video if you've done homework number 9, part 1. Secondly, as far as what you're responsible for test 2 in this class, I would love to make up for the time that we've lost with videos. It's unclear whether the university allows us to do that or not. I contacted the university and I got a message from the president's office saying, yeah, it would just be fine, that's great. But there were a couple other messages out there saying that the university didn't want us to do that. So my main concern is giving you a course that covers the basics. And what I'm going to do is post this video and one other to make up for some material that's considered basic to heat transfer that we missed. I'm not going to make you responsible for it on tests. So this is purely optional. At the same time, I will say anything that you learn related to ideas about radiation or the other video that I'm going to do is helpful as far as understanding. So I encourage you to do this both for your general understanding coming out of heat transfer, understanding the basics, and secondly, just getting good at this material. It will help you understanding. Okay, enough said, let's get to work. So application of this is trying to get something really, really hot, say using the sun. So we've had a lot of success cooking with this pot. We put it outside in a container underneath the sun. It gets really pretty warm. The problem comes up though is that it warms up, it starts radiating a fair amount of heat. So it doesn't quite get as warm as we'd like. How could you take care of that? So this example problem will show you how that actually would work, what kind of surface you would need to do that. But just a quick reminder about what's going on. If we have a surface and we have some incoming radiation, so this would be an example where we have a surface and this incoming radiation is 800 watts per meter squared. That'd be pretty typical of what solar radiation is like. If we want this surface to get really hot, what we would like it to do is absorb a lot of that radiation, but then emit hardly at all. So how do those numbers work? Well, we have the chapter 1 type analysis where we assume that the surface was gray. So a quick reminder on that. No need to write this down. You've seen this all before. Okay, gray means its emissivity and its absorptivity are the same. Some surfaces are gray, not all by any stretch of the imagination. So if the surface was gray, what would we want? Well, looking at that picture clearly, what we would like is we'd like a high absorptivity so a lot of this radiation actually gets in. So that sounds pretty good. In fact, the formula we would have would be the absorbed radiation would be alpha times G. So this alpha, say if it was like 0.96, typical of black paint, okay, that's going to work. We're going to absorb a lot. Same time, there's going to be radiation coming out. When you have a surface near surrounded either by a gas or a vacuum, well, it's going to radiate out. And its emission, it's going to be equal to its emissivity times sigma times its surface temperature to the 4th. Okay, and if it is a gray surface, the emissivity and the absorptivity will be the same. So this number will be high and we'll get a relatively large amount of emission. So gray surface isn't going to work so well. We'll have the opposite problem if its absorptivity is low. So what we would really like is in a case like this is a surface where the absorptivity is high and the emissivity is low. And how could that actually be? Well, it is possible, in particular with a diffuse surface. So we'll talk about that really quickly, remind you what a diffuse surface is. Okay, so diffuse surface. Diffuse surface, in short, is a surface for which the spectral emissivity and the spectral absorptivity are the same for all wavelengths. Okay? The spectral emissivity and the spectral absorptivity are the same for all wavelengths. All right, that was part of homework number 9, part 1, something that you're responsible for understanding. In that homework, I asked you to write down the 2 conditions for which that is true. Okay. An additional note, this condition, diffuse, is true for many, many surfaces. So some surfaces are gray, almost all surfaces are diffuse. So the emissivity, the spectral emissivity, and the spectral absorptivity are actually the same. Okay, good. All right, then a reminder about how we do the calculations, all right, how you proceed. The general rules we have for apply to a diffuse surface. So let's just start with emission. How do you actually get emission from a surface? Well, the first thing we did was, if we have some sort of graph of spectral emissivity, okay, and I'll just have 3 sections just to make it easy. So we'll call this section lambda 1, this section lambda 2, and this section lambda 3. Excuse me, mistake on that. I'm going to call this epsilon 1, epsilon 2, and epsilon 3. So give me just a second, pardon me. Okay, so that might be a graph where we have the different bands of emissivity. Okay, just a reminder, okay, that what we can do is we can calculate the emissivity of the surface at a particular temperature by taking epsilon 1 and multiplying it by the black body fraction from 0 to lambda 1, plus epsilon 2 multiplying by the black body fraction from lambda 1 to lambda 2. And we can keep going and doing that for all the different emissivities that we have. All right. So that's old news. That's easy enough. Once you have that emissivity, you can use that to actually figure out the emission. All right. How about the absorptivity? That has been the part that we worked on recently, and it is kind of challenging. But nonetheless, let me get the basic idea up there. For absorptivity, it's a ratio of how much is absorbed of the incoming radiation to actually the total intensity. So in this case, we would need for this surface to figure out, of this 800 watts per meter squared that's coming in, how much actually gets into the surface, what's absorbed, all right? And what we worked on last time, the last few meetings that we had, is that you can get the absorbed by just going band by band, So you can get the absorbed by doing alpha 1 times the incoming radiation in a band from 0 to lambda 1 plus alpha 2 times the incoming radiation in the band from lambda 1 to lambda 2 plus dot dot dot. Okay, so that is homework number 8, something that you should be pretty familiar with. Good. All right. Well, how to go about getting these numbers? Well, first of all, the alphas. In the homework previously, we had a separate graph for the alphas, but in this case, we don't need it. If we're doing a diffuse surface, then for all wavelengths, the emissivity and the absorptivity are the same. So this alpha 1 will be the same as the epsilon 1 from the graph, and this alpha 2 will be the same as the epsilon 2 from the graph. And why is that again? Because the object is diffuse. All right, so that makes it a lot easier if it's diffuse. We don't need a separate absorptivity graph. What's left then is, how are we going to figure out these G's in these different bands? How do we figure out what's going on? And there's where we end up coming up with a shortcut formula, which works out really, really nicely. All right, so let me erase just a little bit, or add a new line. I'm going to leave this part up here. If we were going to get the absorptivity, okay, what we're going to do is make our first step, instead of making our first step to get G absorbed, we're going to make our first step to get the absorptivity. So once again, the absorptivity is the total absorbed divided by the incoming, okay? And then the total absorbed is this line here that we just wrote, and we would divide this whole thing by the total incoming radiation, and of course we could break that up into separate fractions. All right, so different in how we're proceeding. What you did on homework number 8 is first thing you did was you calculated G for some incoming radiation. And then secondly, you calculated G absorbed for some incoming radiation. And then you took the ratio. All right. What we're going to do in this case is what's more typical out there is we will actually know what G is. It could be gotten by some sort of solar meter that actually points at the sun and gets how intense radiation is. And we're going to make our next step to actually calculate the absorptivity just by thinking about the definition and coming up with this equation. Alpha, the absorptivity is going to be the absorbed divided by the incoming, and we can break it up into a series of fractions. All right? And then the key, okay, is to try to conceptualize what this actually is right here, this fraction right here. Okay, or this section fraction. And there would be just a whole series of fractions where I could box this ratio. All right? This is the incoming radiation that is short wavelength from 0 to lambda, and this is the total incoming radiation. And so what we're looking for here is the fraction or the portion of the incoming radiation that's from 0 to lambda. Now, with solar and some other types of radiation, we can basically say that this incoming radiation is from a black body. The sun radiates like a black body, and a lot of other objects do as well. Well, if that's the case, this fraction of incoming radiation that's that is short wavelength can be calculated by just doing the fraction from 0 to lambda 1. And the same thing here. This fraction right here. This is the total incoming radiation, and this is the incoming radiation that has wavelength lambda 1 from lambda 2. And if the incoming radiation is from a black body, this is the fraction from lambda 1 to lambda 2. And that pattern would go on. So what we can see then is our absorptivity of our surface for this particular radiation, if the surface is from a black body, would be equal to the absorptivity in the first band times the fraction from 0 to lambda 1 for the incoming radiation multiplied by alpha 2 times the fraction of incoming radiation from lambda 1 to lambda 2. And you keep going on that for every single band that you end up having. Let me pause this for just a second.